Thank you to the organizers for the invitation. First time to Russia, enjoying it so far. Thank you all for being here. Okay, so this is joint work with former Russian comrade for many of you, Sasha Razborov, who's at the University of Chicago, different university than University of Illinois at Chicago, but they're close by to each other. Okay, so that's Sasha, for those that don't know him. And the purpose of the talk is to tell you a theorem, and this picture is supposed to describe the content of the theorem. So I learned how to make pictures for this talk, and I'm happy to show off. And we'll get to this in about 30 minutes or so. Okay, so I'll start by introducing Ramsey numbers. And some of you who are familiar and work in the area will find it easy, but for the others, there's going to be some notation that I want to get you familiar with in the first 10 minutes or so. So this is a definition, also a theorem, Ramsey's theorem, and the setup of the talk and of this theorem is that we are speaking about k uniform hypergraphs. K is fixed integer, at least 2. And if you're given two k uniform hypergraphs h1 and h2, the Ramsey number R of h1 and h2 is the minimum number of vertices, capital N in this talk, so that no matter how you partition the k element sets of capital N points in red and blue, you either get a red copy of h1 or a blue copy of h2. And in the case when we are speaking about cliques, and we'll almost exclusively be speaking about cliques, a red ks, this is s points and all the s choose k sets, or a blue kn, we will suppress the notation and just use r sub k of s and n. Okay? And you should think about these parameters, in at least the range of the parameters for much of the talk, as the red subgraph that I'm trying to force on s vertices is typically a fixed integer, not always, but typically a fixed integer, and n is large, and k is fixed. So what's fixed is k and little s, and what will be large is little n and capital N. And of course, one can rephrase the definition. It's a definition, but it's of course also a theorem, right? That such a number exists. And the talk is all about what this number is, and much of quantitative Ramsey theory over the last 60, 70, 80 years is about how big these numbers are. One can phrase this Ramsey parameter in terms of independent sets if we think about the red edges as edges and the blue edges as non-edges. And then a complete blue clique is just an independent set of size n. So I actually looked at the original paper of Ramsey when I was preparing this talk, and it was fun to read it. As many of you know, this is a 1928 paper, London Math Society. Ramsey was trying to prove whether you could show certain first order formulas are true or false. And in the process, he needed to prove this theorem, right? The theorems we actually require concern finite classes. And actually, he proved Ramsey's theorem for about 7 pages of the paper. So he kind of maybe realized that this would be an important maybe one of the most important parts of the paper. And actually after he gave this proof, which is probably the proof that you would give to your students if you were to prove this, or when you prove this in a lecture, he commented that these are probably not the best bounds. And in fact, so in some sense, the question of obtaining quantitative estimates for Ramsey numbers goes back to the original paper of Ramsey. Okay, so what are the exact results in the so-called diagonal case? So this is the case when little s and little n are equal. There are only basically 4. R33 equals 6, R44 is 18. I didn't define Ramsey numbers for more than 2 colors, but you can define it in the natural way, red, blue, and green. And there's one result here, R333 is 17. And for hypergraphs, there's only one result, namely the smallest non-trivial 3 uniform hypergraph Ramsey number R44 is 13. All right, so that means that there's a construction of 12 points where you color the triples, the 12 choose 3 triples red and blue, and there's no complete 4 set that's monochromatic. And then there was a computer assisted proof which showed that if you have 13 points, you cannot do this. So the point is that it's hopeless to determine these numbers exactly, and so much of the research over the many previous decades has been concerned with finding asymptotics. And there's 2 main problems here. One is the so-called diagonal case, when S and N are the same, and the other is the off diagonal case, when S and N are not the same. So in the diagonal case, results from the 40s, 30s and 40s of Erdős and Szekeres prove that this Ramsey number is exponential in n, where the base is between square root of 2 and 4. And despite many decades of work in trying to improve these bases, they remain the same, and there's been some improvements on lower order terms, and the theorem of Conlon for the upper bound and an easy application of the local lemma done by Spencer in the lower bound represent the current state of affairs for the Ramsey numbers. Off diagonal Ramsey numbers are somewhat different. They're polynomial in n, unlike the case of diagonal Ramsey numbers, and today we know the Ramsey number R3n quite well. Classical results of Aytay, Komlor, Semeredi and then Kim in 90s with a construction showed that the order of magnitude is n squared over log n. And as I said, today there have been a lot of improvements. We know this asymptotically up to a factor of 4 using more sophisticated constructions and an upper bound due to Shearer. And when S is bigger than 3, so we are looking for complete graphs bigger than triangles, and for the purposes of this slide you may think of S equals to 4. We don't know anything non-trivial for the off diagonal Ramsey numbers. So both of these proofs are virtually one line proofs if you know basic things about independent sets in hypergraphs. And we have polynomial growth where the exponent is between S plus 1 over 2 and S minus 1 for the off diagonal RSN. When S is 3, of course they match and we get n squared, but for example when S is equal to 4 there's a gap between n cubed and n to the 2.5. It's one of the major open problems. So determining or improving the bounds on the top and on the bottom of this slide would be considered the main open problems in quantitative Ramsey theory for graphs. So that's the situation for graphs. Let me quickly describe the situation for hypergraphs. So the numbers get bigger, so I need to define tower functions. So the tower sub 1 of x is x, and tower sub I plus 1 of x is 2 to the tower sub I of x. So tower sub I of x will be 2 to the 2 to the 2 to the 2 to the tower of 2's, where the number of 2's is 1 less than the subscript in the way I've defined it. And the situation in some sense is worse for hypergraphs. For 3 uniform hypergraphs, diagonal Ramsey numbers, results of Erdős, Heiner and Rado from the 50s and 60s show that RNN is at least exponential in n squared and at most double exponential in n. So there's a gap of an exponent here, and it turns out that for k uniform hypergraphs there's a similar gap. There's of one tower between the upper and the lower bounds. And it turns out that there's various methods in Ramsey theory, both for the upper and for the lower bounds. The upper bound is by some non-trivial pigeonhole argument, and the lower bound is 2 to the n squared is just by a random construction, but there are other exponential constructions. But it turns out there's methods by which you can upgrade constructions and do the pigeonholing as well, so that the main issue for the k uniform numbers essentially is the case k equals to 3. So of course there may be different ways. It may be that something is not true for 3 and becomes true for larger k, but if everything goes as you might expect, and then the case k equals to 3 should govern what's happening. And so perhaps whether this 3 uniform Ramsey number is exponential or double exponential can be considered as the major open problem about the quantitative behavior of hypergraph Ramsey numbers. Yeah, it's a conjecture that it's double exponential. Erdős offered $500 for it. There's been some evidence recently to suggest that this may not be the case. but we don't know. So that's the status for diagonal Ramsey numbers. I have something small to say about that, which is a little result I had with Andrew Sook about 4 years ago, which is this, that we reduced the diagonal Ramsey problem to an off-diagonal Ramsey problem for ordered hypergraphs. So if we define what I call this OR sub 4 P5 of n to be the minimum capital N, so that if I take the numbers 1 through n and I color the 4 element sets with red and blue, and the thing I'm trying to find is a red path of length 5, which is 2 edges which look like that, or a blue clique. So that's what I call OR sub 4 of P5 of n. So P5 is these 2 edges which look like that, and n is just a blue clique. So it's a very simple kind of red object that you're trying to forbid in this ordered Ramsey number. But it turns out that determination of this quantity is equivalent to the 3 uniform diagonal Ramsey problem. So there may be some sense under which you think that off-diagonal Ramsey numbers are easier than diagonal Ramsey numbers for hypergraphs, and I'll say more about off-diagonal Ramsey numbers in a bit. And if you believe that, then this is, gives you some kind of hope that of an approach to prove a construction or a bound for the diagonal case. It's an easy reduction to this question. Okay, so that is the diagonal Ramsey number for hypergraphs. What about the off-diagonal Ramsey numbers? Well, there's a conjecture due to Erdős and Heinal from the 70s, which posits the lower bound on the tower height of these off-diagonal Ramsey numbers. So if you fix k is at least 3, and you fix s is at least k plus 1, because that's the first non-trivial case of a red clique. If s is equal to k, you just want one edge, so that's not interesting. And the conjecture is that these off-diagonal Ramsey numbers grow as a tower of height k minus 1. And I won't say much about the upper bound here, but it's fairly standard and easy to prove the corresponding upper bound. So the upper bound is well known, and the issue is the lower bound. So just to get you a feel for the growth of these numbers, so when k is 3, the conjecture is saying that R for n for 3 uniform is exponential in n, and for k is 4, R5n is double exponential, R6 is triple exponential, and so on. Okay? We know the corresponding upper bounds. So that's conjectured to be the tower height for off-diagonal hypergraph Ramsey numbers by Erdős and Heinal in this important 1972 paper, which I'll come back to. So there was some progress on this. Erdős and Heinal themselves. So before I talk about the larger case of k, let me show you the construction that was given by Erdős and Heinal in 1972, which is a very important construction in the area of Ramsey theory in this questions of this kind. So the case k equals to 3 is known, and there's a construction, and this construction combines randomness and determinism in a very clever and important way. So here's the construction. So you take a random tournament, a random graph tournament on capital N vertices, and then, so that's the randomness. You put, for every I and j, you flip a coin to decide whether I points to j or j points to I. And then you're done with the randomness. Now you make deterministically you make a 3 uniform hypergraph, as I have written. You take 3 points. If they form a cyclic triangle, you put a red hyperedge or a hyperedge. Otherwise, it's blue. That's it. And the claim is that no matter how the orientations were done, you cannot have 4 triples among 4 points. In fact, you cannot even have 3 triples among 4 points. That's what I call k43 with a minus sign. It's a very easy thing to see, but because I'll be coming back to this, let me show you. Suppose you had 3 triples on these 4 points. All the triples must go through one of the points. So that means you must have a cyclically directed triangle on that point for a triple. a hyperedge, and similarly here. So we've put two of them, but now we cannot put the third one that's on this point x, because both of these point out. So the third triple cannot be there. So this means that no matter how you orient, this has nothing to do with any randomness, it's saying it's a fact about tournaments. No matter how you orient pairs, you cannot have 3 cyclically oriented triangles on 4 points. So in hypergraph language, that means there's no K4. And now you have the randomness, and you exploit the randomness to conclude that in any set of approximately logarithmically many vertices, you do have a cyclically oriented triangle. You don't have independence among triples, because you can have triples that share a pair. However, you have sufficient independence in this model to guarantee this fact. And this is precisely what it means to prove that lower bound. It means to give a construction on the capital N, which is 2 to the Cn vertices with no red K4 and no blue Kn. Okay, so this shows that the conjecture is true for k equals to 3, and we'll be coming back to this later. So what about the other values? Well, there's some history here. For general K, Erich and Heinal in their 1972 paper proved that the tower height, the conjecture that they made, is correct as long as the small clique is a constant but not k plus 1, about exponential in k, but you should think of k as being fixed, right? So if when k is 4, this quantity is 7, that means they proved R7n is double exponential in n, for example. And then Conlon, Fox and Benny in 2009 improved this construction to show that it works for S about 5k over 2. And then Andrew Sook and I, and also the same 3 authors in an unpublished work, improved it further to S equals to k plus 3. So there are somewhat different constructions here, but some of you, the astute calculator, may have observed that when when k is equal to 4, all these 3 formulas add up to 7, right? So we get construction for R7n, and correspondingly the higher values of k, but the 2 remaining open cases are R5n and R6n for 4 uniform Ramsey numbers. So those were the 2 open cases. We kind of got obsessed with these 2 cases because, why wouldn't you, right? You're almost there. And so Andrew and I worked, we wrote a sequence of papers for R5n. 2 to the exponential is implicit in this paper of Erich and Heinal, and then we successively improved these lower bounds, and the same for 6. And the upshot is that for R6n we now have a double exponential growth rate. The power of n is not correct, but it's double exponential. For R5n, which is a more difficult problem, right? You're forbidding something smaller, we have 2 to the n to the log n. So here is a summary of what is known for as far as the growth rate of hypergraph Ramsey numbers off diagonal case. We know R5n is 2 to the n to the log n, R6n is double exponential, and we also know corresponding bounds for the k uniform case. So in order to finish off the growth rate of all hypergraph Ramsey problems, only one problem remains, which is to prove a double exponential lower bound for R5n. Give a construction, in other words. I haven't told you how we did these constructions, but the challenge here is in making constructions. Something like we did over there, but it's got to be more sophisticated because we have to control things at the level of log n, because we have double exponential. Okay, so that's the summary of what's known in the graph and the hypergraph case for perhaps the most important problems as far as quantitative bounds go for Ramsey numbers. And now we can get to the subject of the talk, which is to study something more general. And this was the main problem that was posed in this paper of Erich and Heinal that I keep referring to. So what they defined is something a little bit more general than the Ramsey number that I've been talking about so far. It's basically the same thing, except they introduce a new parameter, little t. Okay, so everything is the same except there's now a little t. What is the meaning of this little t? Well, before we wanted a red clique on S vertices or a blue clique on little n vertices, and now we weaken the requirement on the red object that we want to force in this, no matter how you color, and what we want now is S vertices with at least t red edges. So in graph theory or hypergraph theory language, the red objects that you're trying to, the red hypergraph that you're trying to find is a family of hypergraphs, the family of all S vertex hypergraphs with at least t edges. So formally, suppose you're given S greater than k and t an integer between 1 and S choose k, the generalized Ramsey number R sub k S T n is the minimum capital N such that no matter how you color the k sets red and blue, you get something red or you get something blue. The red thing you get is S vertices with at least t edges, and the blue thing you want is a clique. And the reason they are asking this question, or they consider this question, is to get a finer understanding of how these Ramsey numbers behave. So let me just test that everybody has understood the definition, because there's a k, an S, a t, an n, and capital N and an R, which is a lot even for me. So what would this Ramsey number be if the t is equal to 1? Anyone? You want S vertices with one red edge, yes? N. Little n, good. Okay, because if you have little n vertices, no matter how you color red and blue, you either get a red edge, in which case you're done, or everything is blue, in which case you have a blue clique. So when t is equal to 1, this Ramsey number is little n, the smallest possible value. On the other hand, when t is equal to S choose k, of course we are asking for a red clique, and the Ramsey number is the Ramsey number, right? It's the classical Ramsey number. So the question that begs to be asked at this point is, what happens as t grows from 1 to S choose k? And the problem, the main problem in this paper had many interesting things, but they all surrounded this main question, which includes all of the classical Ramsey questions. And the problem was, as you increase t from 1 to S choose k, we know by definition these Ramsey numbers get bigger and bigger and bigger, because you want more red edges. But how do they get bigger? And the conjecture is that they don't smoothly get bigger. They stay as a polynomial until they jump to an exponential, and then they stay as an exponential and then jump to a double exponential, and then they stay and jump again to a triple exponential, and so on until they jump to the final tower height. And actually that final jump happens before S choose k. And actually we've even seen that phenomenon happen right here, right? We jump from polynomial to exponential, and we didn't need the full 4 choose 3 edges for that to happen. We jumped right before, one edge before. And so that's the general problem that they posed, which, given that they knew so little about Ramsey numbers at the time, was an extremely bold statement, that they didn't know any of these Ramsey numbers even in special cases, yet they conjectured this non-smooth behavior. And the main result of this talk is about this question, the very first open case of this question. One cannot hope to solve this question in general, because one would have then solved all the Ramsey numbers that I've been discussing. So the very first open case is the case that generalizes that construction in some sense, the value t1. When does the Ramsey number jump from polynomial to exponential? That was the title of my talk. So what is this t1? It turns out it's not so easy to get a handle at this value. So I need to say a few words to try to tell you when this Ramsey number jumps from polynomial to exponential. It's related to this recursively defined fractal-like function g sub k of s. So g sub k of s is 0 if s is small, it's 1 if s is equal to k, and for s larger than k, it's the maximum over all partitions of s into s1 plus s2 plus sk of the product of the si's together with the sum of the g sub k of si's. So it's a strange thing, but for those who do hypergraphs, it's something that they've probably encountered. What we're asking for is the number of edges in the complete k-partite hypergraph on S points with equal parts. So that would be S1 times S2 times Sk. So Si is about S over k, floor or ceiling. But then in addition to that, what we do, that's the second part of this formula, but the first part means that you repeat what you just did inside each part. And it's this recursion, this fractal behavior, which makes everything complicated. As a combinatorialist, you can understand that this recursion is hard to handle. Induction is harder, things are harder. Asymptotically, the proportion of k sets that you get with this formula is k factorial over k to the k minus k. For people who work in hypergraph theory, you often deal with k-partite hypergraphs. That's a useful technique. And you will know that the proportion of edges that you retain when you take a k-partite hypergraph is k factorial over k to the k. So when k is 2 and you have a graph, you can get a bipartite graph with half the number of edges. When k is 3, you get a 3-partite with 2/9 of the number of edges. So the difference between the recursion and the non-recursion is this minus k in the denominator. You get more edges, a little bit more, but it's that minus k. Okay, so this is just some function. What has this got to do with anything? Well, it turns out, yeah, before I get to it, here are some pictures to try to give you an idea of what the function is trying to count. So if on the left I was interested in counting k4s that are composed of 3 monochromatic matchings, the number of k4s would be G4 of S, right? They'd be one from each or then within the blobs. On the right picture, if you were interested in finding out how many induced pentagons there are in that graph, that's a blow up, it would be G5 of S. Turns out there are several other conjectures in graph theory related to these recursions, which some others have solved, including Bernard Leditsky, and he gave me these pictures. Okay, but these are just to give you a feel for the numbers. What have they got to do with anything? The reason they come up is because Erdős and Heinel proved, and in a surprisingly simple proof, that this first threshold is lower bounded by this value G sub k of S. Now there's a lot of definitions and maxes and mins and so on. So in human language, what they did is they proved that every n vertex k uniform hypergraph, which is sparse, and sparse means every S vertices have at most G sub k of S minus 1 edges, has a big independent set. And a big independent set means polynomial. So the meaning of H of this first threshold being at least G is this statement. And the conjecture, and this is, as I said, surprisingly easy to prove even though it involves this recursion. It's basically you find a complete partite graph and then you just repeat the process within the parts. Since everything is happening at the level of polynomials, you can keep doing this and a polynomial stays polynomial as many times as you want. So that's how this works. And the conjecture, for which Erdős 20 years later offered $500, is that this is sharp. In other words, there's a construction, just like there was a construction over there. What does the construction mean? It means that there is a capital N vertex k uniform hypergraph with two properties, the competing properties that we always have in Ramsey theory. It should be sparse on the one hand, not too many edges. On the other hand, there should be enough edges to make the independence number small. So what is the sparse? Every S vertices span at most G edges. So that's some small number of edges. You can't just have cliques. And there should be enough edges so that the independence number has shot down from polynomial to logarithmic. So that's the conjecture, it's a construction, just like that's the construction over there. In fact, that is the construction for this conjecture when k equals to 3. So right, so here's the case k equals to 3, s equals to 4, the smallest case of that conjecture. So if you think about the case, remember we're increasing s from 1 all the way to 4 choose 3. So if s is equal to 2, if s is equal to 1, we saw that the answer is n. If s is equal to 2, then it turns out that there's results about Steiner triple systems which immediately imply an upper bound that's quadratic in n. If you rephrase this problem, the first problem, then it boils down to saying if you have a 3 uniform hypergraph where every 4 points have at most one edge. In other words, no two triples intersect in 2 points. In other words, it's a linear hypergraph or a partial Steiner system. How large of an independent set are you guaranteed to find? And it's pretty easy to see that you can find an independent set of size about square root of the number of vertices. And if you turn that statement around, you get this n squared. And we know the correct logarithmic factor as well. It's a theorem of Phelps and Rödl. So when t is 2, it's polynomial. When t is 3, we see a construction on the board which shows that it's exponential. So the jump happened, so h1 is 3, and that's precisely this g. Okay? And the question is, can you do this in general? I mean, this g involves recursion, right? I was showing you these fractals, but there's no recursion over there in that picture on tournaments. And the question is, can you do this in general? Actually, Conlon, Fox, and Sudakov in 2010 proved that h equals to g for infinitely many s values when k equals to 3. In other words, they found a construction. What was the construction? You've already seen it, it's that construction. So that construction has logarithmic independence number, we already said that. We already argued that every 4 points have at most 2 edges, but actually every s points have at most about 1/4 s choose 3 edges. That's a very simple exercise. So here's the idea, the main issue is how many directed triangles can you have on s points, because that's how many edges you have, right? Because the hypergraph is going to be the directed triangles, just like it was over there. And you can calculate that exactly. It turns out to be quarter s plus 1 choose 3. And just as a beautiful coincidence of numerology, when s is equal to 3 and for infinitely many s's, that's exactly the formula you get with doing that recursion for infinitely many values of s. So it was really beautiful and fortunate that the random tournament, which has no recursion inbuilt in it, gives you a formula which is equal to the formula given by that complicated formula. Okay. But unfortunately, this does not work for larger s, so you really need to do it with the recursion in general if you're going to try to mimic this approach. Okay, and that's what we managed to do. So this is our main theorem with Razborov, that for k at least 4, h of k equals to g sub k plus 1. In other words, there's a construction, it's sparse, it has logarithmic independence number. Why was it difficult? It was difficult because of this fractal like nature in the definition of g. So we had to overcome this issue somehow. We had to come up with a problem. So the problem that they came up with in this case was, if you have a tournament, how many directed triangles can you have? And the answer was 1/4 s choose 3, and that happened to be the right formula. And once you've come up with a problem, a suitable problem, you can randomize it, just as we did over here, to solve this Ramsey question. So actually all we had to do to solve this question is to make up another question. We had to come up with a question whose answer was really the recursion and solve it. So that's good. You don't have to solve a problem, you can come up with your own problem. So we can suddenly have a lot more freedom, you can do anything you want, right? Make up your own problem, and that's what we did. But the question was, how do you come up with a problem whose answer is recursion? So I do extremal combinatorics. I said, what do I know in extremal combinatorics? I know extremal graph theory, and it's a big subject, open for questions for many decades. But the point is that in extremal graph theory, and here's a typical theorem, the answers to these extremal questions are blow-ups of small structures. So it's Turan's theorem. Here's a more complicated theorem about color critical graphs. You have some extremal graphs, but they're all blow-ups. There's no recursion, right? So I mean, if you take Turan's theorem for k4, this is what it says. It says the maximum number of edges in a graph without k4 is the number of edges in that graph. That has density 2/3. You want to do something like this, right? But it doesn't make sense because you have cliques. So extremal graph theory doesn't easily give you these recursive things. So okay, extremal graph theory doesn't work, right? How do we obtain questions where the answer may be a recursive construction? Graphs don't work. Hypergraphs are much more complicated things, but it turns out that many basic conjectures about extremal hypergraph problems do have recursive structure, exactly the kind that we need in this g sub k of s. But we don't know the solution to any one of them, right? Just like I said that the number of triangles, directed triangles on S points is quarter S choose 3. We don't know the answer to this question for any problem, one problem for hypergraphs. So that was not very encouraging. But there's one thing more you can do, which is you can look at graph theory, but look at induced structures. And there's a fertile ground to try to find problems whose answer is given by these fractals. And that's what we did. So I need a definition, which is this. Given a k-vertex graph R, like the pentagon, the inducibility is the maximum number of induced copies of that graph in any graph. And I normalize it by the number of total number of k sets. Okay, so the only difference between this and classical extremal graph theory, Turan's theorem, is you're interested in induced copies, not in just copies. And why is that good? Because it turns out that there's a beautiful conjecture in the area by Golombek and Pippinger from the 70s, which posits what this extremal induced density is for the cycle of length k. It says that the inducibility of the k cycle is k factorial over k to the k minus k, and you should recognize that formula from the recursion that I've been discussing. The example is the recursion. This is open. The best known general result is by Kral, Noreen, and Volets, which is off by a factor of about 2. However, when k is equal to 5, it is known by an intensive use of flag algebras. Balogh, Hu, Leditsky, and Fender in 2016 proved this theorem. Now, there's a clear lower bound given by the pictures, right? This particular graph has 1 over 26 proportion of induced C5s, but the challenge is to get an upper bound. And so one way to prove the Erdős-Heinel conjecture would be to prove the Golombek-Pippinger conjecture. So actually the first thing I did in this area is I observed that this implies the Erdős-Heinel conjecture for k equals to 5, using something similar to that. But then we said we should try to do the whole thing, and eventually we did. So it turns out that we need to deal with, we need to be functioning in a richer theory than just the theory of graphs. Although theorems should be true about induced graphs, they're tough to prove. So we needed to have a theory which involves colors, involves directions, involves more things which will allow us to deal with the technical aspects of the proof and still get the same result. And this is how we came up with this problem. So the setup is that you have directions, just like we did in the tournament, and you have colors. So if you have a k-vertex hypergraph, let's say a k-vertex graph, it's a tournament, directed graph, let's say this is it, fix that, let's call that R. It can be whatever you want, it can be a transitive tournament like I have shown, it can be any other tournament you want, fix your tournament that you like, and fix 6 colors, okay, 4 choose 2 colors, k choose 2 colors, and color this with those 6 colors in a prescribed way. And now the question is, if I give you an n-vertex tournament whose pairs are colored with 6 colors, the same 6 colors, what's the maximum number of copies of that you can have? And there's a lower bound construction, that construction, which is g sub k of s, and the theorem is that that's the best that you can do. And once you do this, it's a simple exercise, in fact I'll show you this proof, to prove the Erdős-Heinel conjecture. Let's prove it. Let's prove the full conjecture. That there's a hypergraph which is sparse and has logarithmic independence number. I have to give you a construction. Let me do it as follows. I take n vertices, I fix a rainbow tournament, I take n vertices just like I did with that tournament, and I do something randomly. I randomly color the pairs with k choose 2 colors, 6 colors if k is 4, and I randomly orient the pairs in a random tournament. So I have a colored random tournament, and I make a hypergraph. What is a hypergraph? When is a k element set a hyperedge? If it induces a copy of R. Now I made a hypergraph. I claim this hypergraph has 2 properties, the hard property and the easy property. The easy property is that the independence number is logarithmic in n. Again, you do not have independence among k sets because they share things, but you have sufficient independence to guarantee that the independence number is logarithmic in n. That's an easy exercise. What's hard is that every s vertices have at most g sub k of s edges. Why is that true? That's precisely this statement. Every S vertices have at most G sub k of S copies of that, and each copy is an edge. So that's basically what we did, and it's not clear that this is the only way to do it. You could come up with other extremal problems to have the same effect. So finally, why did we do this? You know, why? Well, we tried the easier things, namely dealing with graphs, dealing with Golombek-Pippinger conjecture and related problems, but somehow, and this is hard to describe unless you've worked in this topic, the kinds of inducibility theorems that one is able to prove are ones where the structure that you're trying to force is very asymmetric. So one problem in the case of cycles is that if you have an edge and I tell you it's in a 5 cycle or in a k cycle, you don't know which edge it plays the role of in the cycle. And when you try to prove a theorem about the structure in a big graph, this is a problem because you don't know what things look like. But now consider a big coloring of a graph, and if I give you an orange edge that's pointing in that direction and I say let's look at the copies of the R that this edge is in, you know that it's always going to be the orange edge in the R because there's only one orange edge. You even know how the things are going to point. So this is helpful. In fact, there have been some recent results on inducibility of random graphs by Euster and Fox, Huang and Lee, and they required very asymmetric properties of their small structure, trivial automorphism group and even more things, and somehow the rainbow tournament is designed to make everything easy in terms of technical aspects of proving this theorem. And so in some sense that was there were two aspects to this project. One was the difficult one in some sense was coming up with the problem, and then of course you have to solve it, but it's been designed so that you can solve it without too much difficulty. And that's all I have. Thank you for your attention.